Hello, this is Mrs. Sargent, and this is the notes for AP Chemistry on March 7th, 2018. There's several students that are going to be gone on a field trip, so I'm creating a video for Wednesday's notes. Please keep in mind that if you need to pause the video to get things written down, that's one of the benefits of having a video is you can just hit that pause button as you're going through it. So last class we ended with talking about the types of bonds and the ionic character of a bond. Today we are starting what is from chapter 8 in section 8.7, and we're just going to introduce what are models. So in general, any type of models, they are attempts to explain how nature operates on the microscopic level based on experiences in the macroscopic world. So this especially applies to science, but even microscopic can mean different things, thinking about what our focus is. So with chemistry, we're thinking about chemical bonds and molecules, where the model of something else might just be pinpointing one aspect of something that is larger. So it's just an attempt to explain it based off of what we see with the whole world. So bonding is a model proposed to explain molecular stability. So here we have a model for a methane molecule. You can see the carbon in the center, and it is bonded to 4 hydrogen atoms. So remember that the chemical bonds are forces that cause a group of atoms to behave as a unit. So these bonds between the carbon and the hydrogen are causing this to behave as a unit. The bonds form in order for the system to seek the lowest possible energy. So instead of thinking of a molecule like methane with stabilization energy of 1,652 kilojoules, we might think of CH4 as having 4 of the carbon-hydrogen bonds. And so if the whole molecule is 1,652, then we can divide that stabilization energy by 4 CH bonds. And that is going to give us a bond energy between each hydrogen and the carbon of 413 kilojoules per mole. So this is kilojoules per mole of CH4, but we're trying to figure out what it is for each bond, and so we divide that by our 4 carbon-hydrogen bonds to get our bond energy for each of those same bonds. So models continued. Remember that in natural processes, there is a tendency to go towards the lower energy. So lowest energy possible is good, and nature's going to go there whenever possible. Also, remember that models are not reality. And what I mean by this is it's a representation of something. It's not reality. It's not what we actually have. These are human inventions. That's what models are. Models are often wrong. So often we get caught up in, well, it has to be just perfect. Well, that's part of science, is that it's not going to be just perfect. Oftentimes when we use models, we oversimplify the explanation. And so because of that, we might leave out important details when we oversimplify it. Excuse me. And so then the model is wrong. And so that might also mean that our models have flaws. But the beauty of these flaws, and when it is wrong, is that we patch it. We try to fix what's wrong, what's not working. We patch that, and then we add more details. I don't know what just happened here, but I'll finish up these last 2 bullet points. Models are often based on assumptions. And so the most important thing is that wrong models help us to learn what is right. Sorry, I didn't realize that going forward was going to, and then backward was going to take away these previous bullet points that were recorded. I'm recording on my Mac at home, so it's a little bit different than my school computer. So covalent bond energies and chemical reactions. So bond energies are really an average of the individual dissociation energies. You can see an example on page 322 where the carbon-hydrogen bond energy is not the same every time. So it's an average is what we saw with that 413 kilojoules. Average bond energies, these are in table 8.5. And on page 323. So we have single bonds in that table, and we also have multiple bonds in that table. There is a relationship between the number of electrons shared and the bond length. So between two atoms, as the number of bonds increase, the bond energy is also going to increase. So there's a direct relationship there between the number of bonds and the bond energy, and that is going to mean that we have shorter bond lengths. So here is in the newest edition of the book, this is table 8.5, no longer 8.4, but 8.5. And that's what is on page 323 in your book. So we have our single bonds listed here, and then we have multiple bonds. And so there is different bond energies if you have single bonds versus multiple bonds. You can see this with N bonded to another end is 160 kilojoules per mole with a single bond. With a double bond, it's going to be 418 kilojoules per mole, and then with a triple bond, 941. So there is a difference depending on the number of bonds there. And so there is this exception for the carbon double bonded oxygen is 745 unless that carbon double bonded oxygen is in CO2, and then it is going to be 799. So bond energy and enthalpy. Bond energies can be used to calculate the approximate enthalpies of reaction. So breaking bonds is going to be endothermic. That's something that you need to remember. So that means that we're going to have a positive value when we're breaking bonds for our energy. When we go to form our bonds, that is an exothermic process. And so that is going to be a negative energy value. So in order to calculate delta H, it is going to be the sum of N is your number of moles, and D is your bond energy per mole. So for each mole, the bond energy from that table, 8.5, which D is always going to be a positive value. Minus the sum of the number of moles for the bond energy per mole that is formed. When our bonds are broken, this is coming from the reactants side. And when we are forming bonds, this is the products side. So notice that that is a flip from our previous energy, or our previous enthalpy, where we had the sum of the heat of formation for the products minus the sum of the heat of formation for the reactants. So there is a slight change when we're looking at the bond energies in the order we're talking about. So let's take a look at a couple of examples. Again, this is now table 8.5, no longer 8.4. So you're going to need that for reference in order to do these calculations. So we have hydrogen gas and we have chlorine gas that are reacting to form 2 moles of hydrochloric acid. So I just kind of want to draw out, what do we have going on here? What's happening? So we have our hydrogen molecule, and then we have our chlorine molecule. And so that's going to form 2 molecules, or 2 moles of our hydrochloric acid. Okay. So what happens is the reactants, we have to go in here and we have to break the bonds in our reactants, and then we are forming the bonds in our products. Okay. So the equation, we have delta H equals the sum of our reactant bonds broken minus the sum of our product bonds that are formed. That's kind of generalizing that equation that we looked at on the last slide. Okay. So we need to look up in our table some different values. And I'm going to write this out so that we have delta H is equal to the sum of our HH bond plus, because sum is adding them together, our Cl bond minus the sum of, remember we have 2 moles there, so we got to multiply by the coefficient, our HCl bond. Okay, so that's what we're looking at. So when I go and I look at table 8.5, I find that the bond energy for the hydrogen-hydrogen bond is going to be 432 kilojoules per mole. And the Cl-Cl bond is going to be 239 kilojoules per mole. So that's the sum of my bonds that are being broken. And I'm going to subtract 2 times my hydrogen chlorine bond, which happens to be 427 kilojoules per mole. So when I do this calculation, I find that my delta H is equal to negative 183 kilojoules. Okay, so that is for letter A. For letter B, oh, the lines disappeared on this one because they were written in there. So we have 1 molecule of our nitrogen, which has a triple bond between it, and you would be you would need that information at this point to know how many bonds there are there. And then we have 3 molecules or 3 moles of our hydrogen-hydrogen bond. And it is going to form 2 moles of our NH3 bond. Okay, so we have our visual there. So this is going to be equal to, for delta H, is going to be equal to the sum of our triple bonded nitrogen plus 3 times our hydrogen-hydrogen bonds. Minus the sum of 2 times our, we have 2 moles of our NH3. Now, it's important to note that we have more than just 2 atoms in this NH3 molecule. We have 4 atoms total. So we have a total of 1, 2, 3 NH bonds in each of these molecules. So it's going to be 2 times the 3 NH bonds. So we're going to have to multiply our bond energy for NH times 3 and then multiply it by the number of moles. So why don't you pause the video and give this one a try. Okay, welcome back. I hope you paused that video and you gave this one a try. So here is our delta H. The triple bond energy for the nitrogen-nitrogen bond is 941 kilojoules per mole. And then we are adding that to 3 times our hydrogen-hydrogen bond, which is 432. So those are the bonds that are being broken in the reactants. And we are subtracting from that, we have 2 times our 3 NH bonds. And the NH bond has a bond energy of 391. Okay, so I kind of put in my parentheses there to help us with our order of operations. This, I broke this down and I did the bonds broken, which was 2,237, and then I subtracted my bonds that were formed, which was 2,346 kilojoules. And when I finished off this calculation, I ended up with negative 109 kilojoules for my answer. So in order to do these calculations, you need a table that is going to give you your bond energies. And then it's just looking at how many of those bonds do I have in my molecule, and then how many moles of that molecule do I have. I'm plugging it into the equation. The last thing that I want to look at is this asks us to compare our answers from parts A and B on the previous example with the delta H values calculated for each reaction using standard enthalpies of formation in Appendix 4. So in Appendix 4, we use this during one of our previous chapters when we were looking at the heats of formation and then figuring out the enthalpy for the reaction. I believe that was chapter 6. And what it's asking us is, do the enthalpy changes calculated from the bond energies, which we did on the last slide, give a reasonable estimate of the actual values? So just as a reminder, delta H of the reaction is equal to the sum of the heat of formation for the reactant, or the products minus the sum of the standard enthalpy heat of formation for the reactants. And so this is what I was saying, is that there's a difference in what is being subtracted from what in regards to products and reactants with the last example. So I'm going to look up in that table, and for A, we had the hydrogen gas, chlorine gas produces 2 HCl. So I look up the HCl enthalpy. Oh, I forgot that I was going to do that. Dang it. So this is for A. And delta H, I'm going to have 2 times the heat of formation for HCl, and then I'm subtracting the hydrogen and the chlorine that are added together. Okay, so when I look this up, the heat of formation for hydrochloric acid is negative 92. One thing that's important to remember is that we said elements in their natural state are 0. Well, hydrogen is naturally diatomic, so that's going to be 0. And chlorine is also naturally diatomic. So we don't really have to worry about our reactants in this one. So 2 times negative 192 is going to give us negative 184 kilojoules. Okay, so how does this compare to what we had in our last example? We got negative 183 kilojoules from our bond energies. So that is pretty close for the heat of formation versus the bond energy. So that is a reasonable estimate. Then for the letter B, we had our nitrogen and hydrogen gas reacting to form 2 molecules of NH3. So we're going to do 2 times NH3 minus hydrogen and nitrogen, and the sum of those. But remember that hydrogen's in its natural state, nitrogen's in its natural state, so those are both going to be 0. So we need to take 2 times the heat of formation for NH3, which is negative 46 for that. And so when we take 2 times the negative 46, we get negative 92 kilojoules. And what we got on the last example for the bond energy is we got negative 109 kilojoules from the bond energy. Wow, that's so that one's not quite as close as the letter A example, but we're still within 17 kilojoules, so it's not that far off. I would say that that is also a reasonable estimate because it's an estimate, it's not exact. The thing that you have to remember is that you have multiple bonds in NH3, where with hydrochloric acid you just had a single bond in there. And we talked about that the bond energies is an average between all of the bonds. And so that could be what's causing the bigger difference between our heat of formation and the bond energy calculation for enthalpy. Okay. So that's where we're gonna stop today. Your homework for Friday. So I believe this is homework number 4 from chapter 8. Is going to be numbers 70, 72, 74, and 76. Okay, so Friday we're going to talk about Lewis structures, and then next week we're going to get into building some models based off of our Lewis structures. So please take a look at this. Come in and ask me questions. We can talk about that at the beginning class on Friday. But thank you for taking the time to do this, and have a great day. Bye.